It's a fairly well known fact that sticking a fork in an outlet is deadly, but why? It's an easy thing to gloss over in our busy lives, but it's good to question these types of things that have seemingly obvious answers. But before we answer that question, we need to first ask, what even is electricity? Electricity, in basic terms, is the flow of charged particles that are capable of doing work. In most cases, these charged particles are electrons, which are the particles in the atom that float around the central nucleus. These charged particles can perform tasks such as lighting up an LED, powering a car, or even sending signals throughout your body. That last bit is important because these signals can be easily disrupted if they come into contact with any outside electricity. So, a logical line of reasoning from this is if electricity can be used to create malfunctions in the body, then surely it's something we should always try and avoid. But there are a few factors that can determine how dangerous electricity can be. Critical ones are voltage, resistance, and current. You may notice that basically every battery out there has what's called a voltage rating, but what does voltage even mean? It's a common misconception that voltage is a unit for measuring energy, but this is actually not the case. Energy is typically measured in joules, which is not what is describing voltage. Another common misconception is that voltage is power. Power is a measurement of energy over time. So, what exactly is voltage if it's not energy or power? In crude terms, voltage is kind of like the driving force that pushes electrons from one side of the battery to the other, and it's measured in volts. The real explanation for what voltage is actually goes way deeper than this, but for the purposes of answering our question, this explanation will have to suffice. Resistance is another important concept to consider. Resistance is measured in ohms. The resistance of a material basically describes its ability to conduct electricity. Materials that are great conductors are called, well, conductors. Materials that make poor conductors are called insulators. We can vary the resistance of conductors by sprinkling in a little bit of insulator in them. For example, the manufacturers of our 1K ohm resistor achieve that resistance by placing some carbon atoms in the typically iron wire, creating what's called an alloy. We can use the resistance to limit the current of a circuit. What is current? Current determines the flow of electrons over a given time. Current is measured in amperes, but normal people just call them amps. And in simple terms, it measures how quickly electrons are moving. The easiest way to remember all this is to imagine a man riding a bike up a hill. The effort he's exerting is kind of like the voltage, the incline is like the resistance, and how quickly he's traveling is like the current. For another depiction, let's say we have a simple circuit where we have a 4.8 volt battery that's connected through an LED through a 1K ohm resistor. The current would be 4.8 milliamps. Why? Well, we can derive this value through Ohm's law, which is a neat formula that describes the relationship between these three concepts. The voltage is equal to the current times the resistance, and in this formula we find that lower voltages and higher resistances lead to less current, while higher voltages and lower resistance leads to more current. Keep this in mind for later, it's going to be important. In our example, if we replaced our 4.8 battery with another battery that has a greater voltage, the current flow to the LED would lead to the LED burning out, straight up destroying it forever, which leads to another important observation. If the current gets too high, then stuff starts to break down. So, how does all this relate to the human body? Well, the body is a bit like our circuit, where it has a natural resistance, the skin, and other insulators in the body that protect it. But if the applied voltage gets too high, then the current becomes so great. Remember, current goes up as voltage goes up, that the body will shut down. If you find yourself in the unfortunate situation where you are a part of a circuit where the current is 10 milliamps, generously assuming your skin is decently dry, you will feel an intense shock. At these current levels, your muscles will involuntarily contract, meaning that if you are gripping the connections connecting you to the circuit, you may not be able to let go, leading to worse injuries. And in this case, you will suffer intense burns both on your skin and inside your body, though you will likely live to tell the tale. If we ramp this up to 100 milliamps, ventricular fibrillation of the heart occurs, which essentially just means that the muscles in your heart palpitate in an asynchronous manner, leading to no blood being pumped, and this would ultimately kill you. So we know generally at what current levels you will die at, but what about the voltage? At what voltage does the fatal limit lie? The answer is actually quite complicated, since we know from Ohm's law that greater resistance leads to a lower current, and the resistance of skin varies from person to person, and depending on how moist a person's skin is, the resistance can vary drastically. But what makes this nearly impossible to pinpoint is the fact that as current flows into a person, their skin burns and breaks down, lowering the resistance of the skin and shifting the lethal limit. Humans can survive up to a 300 volt voltage of searing pain with burns, although if they hold on for too long, there is a risk of the muscles contracting involuntarily and worse injuries. But it is possible to survive, although it's not recommended that you ever attempt to hook yourself up to a 300 volt battery. I certainly didn't, in the making of this video, and nor should you. Please be safe, but do your research. So back to our question, we should probably find out what the voltage of a wall outlet is, and it turns out the voltage of a wall outlet, at least in North America, is 120 volts. What? How is it possible to go from 300 volts causing burns and the potential for worse injury to 120 volts definitely ending someone's life? Well, the answer lies in the type of current. Up until this point, we were only talking about what's called DC, or direct current, from a battery, but wall outlets use what's called AC, or alternating current, not air conditioning, alternating current. In DC, the current remains at a constant value. So in our first example with the light circuit, the circuit would be at a constant 6 volts, meaning that if we just let the circuit run, it would never deviate from the 6 volts. It's like a constant line. In AC, the current oscillates between negative and positive voltages in a wave-like manner. The values deviate, and they slowly will go down and up and vary at a consistent rate. But this is a bit of a conundrum. In the 300 volt DC example, we are at a constant plus 300 volts for as long as the body stays connected to the power source, while with our outlet, we oscillate from positive 120 volts to negative 120 volts. If we go back to our LED example, making sure to increase the resistance of the resistor to make sure that the LED doesn't burn out and straight up break on us, then the LED would shine way brighter for the 300 volt DC example than the 120 volt AC, signaling that it's applying more current. And it is, but there's one flaw in correlating the LED circuit to the human body. The human body acts like a giant capacitor. Okay, so what is a capacitor? Take two large plates, make sure that they are made of a conductive material, and between them, place an insulator. Connect one of the plates to the positive side of the battery and the other to the negative side. Electrons will flow out of the battery onto the negative plate of the capacitor, and the surplus of electrons on one plate will repel the electrons on the other, leading to a complete circuit where electrons flow from one side of a battery and electrons flow into the other side of a battery. But this only lasts for a short period because only so many electrons can fit onto the negative plate, thus resulting in only so many electrons that can be repelled off the positive plate, leading to a system where the output current starts out the same as the input, but exponentially drops as time passes. If we were to hook this up to our LED circuit, the LED would be bright immediately after first connecting up the circuit, but it would dim as time passes. If we hooked up a capacitor to AC, the negative plate of a capacitor would fill up with electrons, leading to a high output current. But as the output starts to dissipate, suddenly the positive and negative switch, and electrons flow from the other side into the capacitor. And since there is now a lack of electrons on what is now the negative plate, electrons can easily flow into it again. And this process repeats over and over, which leads to another crucial observation. Capacitors eventually block out DC, but they always allow AC to pass, which leads us back to the body. The reason why wall outlets are lethal is that they use AC so they can overcome bodily capacitance at a high enough voltage to overcome the resistance of the skin. And that's it. Thanks for watching. If you enjoyed it, do all the stuff, like and subscribe, please. Okay, bye.